benvenuti a Giovedì Scienza.
Good evening. Welcome to Giovedì Scienza, Wealth Science on a Thursday. Welcome to all those who are following us on the streaming version or those who will be watching our conferences through the net, even in the future. This evening is a very special meeting, the one you're about to attend, with Pierre Léna, who's a French astrophysicist, very well known, and a pioneer in many fields. Certainly in some of the fields of astronomy, and in particular for infrared astronomy. But he was also a pioneer in the field of technologies, in the field of astronomy. One of the adventures he will be talking about this evening is really outstanding. He was the astronomer who managed to see the longest possible sun eclipse on our planet. Usually it's 6.5 minutes when it can't go beyond, because of reasons linked to the celestial mechanics. But if you fly in a very fast plane, say the Concorde, unfortunately we haven't got it anymore, we haven't got any supersonic planes, but then you will be flying at 2.2 times the speed of sound, a bit less than maybe, and therefore he was able to follow it for 74 minutes, not just for the fact that he wanted to see it for a longer time, but because it meant that various researchers from various countries in various continents to carry out studies from an extraordinary point of view. That is to say, 17,000 meters above sea level. Another extraordinary thing he has done is to develop infrared astronomy. That is to say, the astronomy that enables us to see the sun and nebulae and the universe in a wavelength that we can't see with our eyes, but which is very interesting because nebulae, for example, forming stars in formation or planets in formation, emit infrared radiation. So if we want to study them, we have to watch them seeing, so to speak, this wavelength. And he has been a pioneer in this field. Not only this, other technologies, for example, optics, which continuously adapt to the situation, that is to say, adaptive optics, one of the fields which he's been involved with. And lastly, and with this I will conclude this very brief presentation, which should be a much longer presentation considering he is a member of the Académie de France, but there's something which is a bit different, but which is at the same time the most interesting one, because science is a very beautiful thing, but to disseminate science amongst children is even more important. And Pierre Léna is in charge of a French program for schools, which is called La Main, la Pâte, and it is a program which he started with Georges Charpak, who was a Nobel Laureate, and he continues this program, which he started off with Charpak, who is now no longer with us. There are boxes of materials which are then handed to the teachers. That means that they can carry out experiments, and the criterion is that if you do, you will understand and remember much better. So to carry out experiments means that you will learn more, enjoy it more, and remember it for a longer period of time. And that was what La Main, la Pâte does to disseminate science and encourage young French people to enroll in scientific faculties. And this is what we are doing in Italy. For example, Professor Pascucci works with a very similar program. There are various ones. And Turin, if you remember, not only for schools, to all the community has been working both with Experimenta and with the Laboratori della Curiosità Perché, the Laboratories of Curiosity. Why? I would also like to thank, lastly, the French embassy that contributed to his trip and made it possible for him to be here today. And I would like to thank also the French consul in Turin. Thank you very much. The floor to you, Professor Léna.
Buonasera, signore e signori. Je ne suis pas responsable du titre.
I am not the person who is responsible for the title. I think it's Bianucci that chose the title, which means following the shadow of the moon, the adventures of a supersonic astrophysic. Adventures in the plural because there's more than one. This one took up about a year of my life, but there are many other things too. So I've decided to put my presentation together and to talk about the exploration of infrared light. Corneille had defined light as this obscure light that falls from the stars. It's obscure because you can't see infrared, but it is a form of light, which means that it can shed light and help us understand the various phenomena that have infrared. Infrared was discovered by William Hersch, who was a very famous astronomer who also discovered Uranus in the 1800s. It was a very simple experiment, one of the experiments that we can get primary school children to do to show that the world sometimes hides very interesting mysteries that have to be explored. He created a thermometer of the solar spectrum, seeing that the temperature of the thermometer, as you can see here in the image, continues to increase even when it is outside compared to the array of the visible beyond the red. This light, which the human eye can't see, but which bears information that comes from the sun, this light is something we don't perceive with our eyes, but with our hand. The cells of our hands, skin, are sensitive to infrared. The feeling of heat, of red light comes from the energy which this infrared radiation has. This infrared light was of great interest right from the beginning, but it's very difficult to identify, so much so that until 1950, 1960, that is to say, the time when I began my career as a scientific researcher, up until then we had no clear idea of the sources of the infrared in the sky, except for the sun and possibly stars. But no astronomer had measured the amount of infrared energy that had been produced by stars. Infrared has a very interesting property. That is to say that the cold objects that do not emit visible light emit infrared radiation. To observe objects, cold objects, it is the only light that can be used. So it's very important for astronomers. If we observe an object, an astronomical object, such as Andromeda, the only galaxy that we can see from the northern hemisphere, well then, that galaxy observed, and here you can see the photo, it's top left, you can see the stars and the image of the galaxy through the visible light. But there are other lights as well as the visible light. Each one of them offers us a different view of Andromeda. Here you see top right, you can see it in the infrared. You can see that it's very different as compared to the one top left. Its color is not the real one, because otherwise we couldn't see it. We couldn't see the colors of the infrared, but it's more intense and the more intense it is, the stronger the radiation is. But there are other lights which astronomers in the past 50 years, thanks also to access to space via satellites, are able to measure, and which offer very important information on astronomical objects. Bottom right, you see, is the same Andromeda, which is observed with X-rays. You can see that it is virtually only a point, that is to say, the center, the nucleus of the galaxy, which contains a black hole. And further on, we will find this black hole. Then there are other wavelengths, for example, radio waves that are not represented here, or the distant infrared. Every time, this gives us a very different image of the galaxy with the useful information on the temperature, on the composition, on powder, temperature of gases, and so on. Therefore, the infrared is especially precious, but it is not the only radiation. To identify these lights, and in particular the infrared light, we must use very many different telescopes that give us the images that we've just seen. For example, the Herschel telescope that bears Herschel's name, as we saw a moment ago, is an observatory of the infrared image, which the European Space Agency has placed or positioned. This observatory, it is right to say it here in Turin, is in a point of space that is the opposite of the sun seen from the Earth, and which accompanies the Earth in its yearly revolution. The observatory remains in the same position compared to Sun and Earth. It is a point which is called the Lagrange point. Luigi Giuseppe Lagrange was born in Turin and lived here throughout his childhood and youth, and then went to Berlin and later to Paris, where he died. He is the one the observatory is dedicated to. I would like to say something about Lagrange. The Turin Academy of Science, if I'm not mistaken, was established by Lagrange when he was 22 years. It was a time there when a youngster, even though only 22, could establish an Academy of Science. For example, the Académie des Lycées was also created in 1603 by an expert, a scholar who's only 18. It was a time when creativity was stimulated and appreciated right from youth. This is what I would like to also talk about further on. Here you see telescopes in space, telescopes on the ground. This telescope was established by Canada, France, and Hawaii. It's in Hawaii and has been working for the past 30 years and gives us some wonderful images on the rotation of the Earth with these traces of stars. More recently, we have another telescope which is the one able to identify radio waves, which is a form of light. This telescope is based in Chile. It's more recent. It was opened only 3 years ago. And it combines light with various antennae. I mean, it's an interferometer. It gives very detailed images. Here you can see 4 of these. There are 64, which make it possible to plot very precise maps of astronomical objects according to the wavelength of these radio frequencies. I will show you soon a very beautiful map which we kept with this instrument. We have a very big diversity of telescopes, very different technologies that are being used, but to remain within the framework of the infrared, let us see what we did 40 years ago. At those days, there were no satellites. There weren't any in Europe or in the US, or at least there weren't any satellites able to observe infrared radiation. So we had to travel above the clouds above the aqueous vapor that absorbs most of the infrared. We decided to use a caravel. There are not many of them left. It was a bioreactor which was built by the French Aerospatial Agency, the same one which then manufactured Concorde, and we set up a telescope on it instead of one of the security exits or safety exits. You can see it here in the picture. I put the image of this well-known European astronaut, Claude Nicollier. He was Swiss, who flew for the European Space Agency in 3 missions. It was on this one and on other spacecrafts. And he had to repair the Hubble telescope, which had some problems, and there were some design flaws. And he was with us on this plane. He had come as an astronomer. What were we doing at the time? Something which is still very topical, which you do with very much more powerful machines. We explored these molecular clouds that are in our galaxy not far from us. And which are some star nurseries, so to speak. That is a place where gas and dust, because of gravitation, attract each other, forming not only stars, but also a trail or cortege of objects, including planets. We will be seeing them in a moment. And light, visible light, cannot pass through these waves, but infrared can. And this means that we can see what there is inside these clouds, these molecular clouds. This is called S140, and we observe it with the infrared. And here you can see it. It's been seen by a team at the German Max Planck Institute. This is a star which has just been formed in this cloud, not yesterday, not the day before, maybe 100,000 years ago or millions of years ago, but because the process of the creation of the star is a very rapid process, not more than 1 billion years. Then the star, like our sun, can continue to emit its rays at least for 10 billion years. This at least is what has happened with the sun. These nurseries were observed with the caravel, while today they are followed with the Herschel satellite, which supplies wonderful images that you can easily find also on the net. And now I would like to show you a clip of a film that was carried out by Cambridge researchers in Cambridge, US, Harvard, these are the images of a collapse due to gravity of a molecular cloud made of dust. And you see all the reds and yellows, which corresponds to the density of the matter according to the measurements that are below. Here you can see the denser material that has formed a sort of cluster, and you can see at top right time, and you have about 200,000 years, and 200,000 years this round cloud changes and develops very complex forms, but there are clusters, globes which form. You can see them. These are protostars, that is to say areas where matter accumulates and is hot because the fall frees gravitational force, and it forms some eddies alike. And you can see not only the star which is in formation, this is a digital simulation with the computer, but you can also see a sort of disk which rotates. This disk is what starts the planetary systems. And that is how our system developed through the collapse of a gravitational cloud, or it is a contemporary of Lagrange, Mr. Laplace, who was born near Savoie in Bourgogne, who was the first to suggest this mechanism of collapse due to gravity as an explanation for the origin of stars. So to create, in the case of Laplace, the solar system. Laplace spoke about the system of the world. We have great evidence of the fact that the mechanism described by this digital simulation is the mechanism which is what underlies the creation of the planets and the sun. It happens very quickly. I did not mention the scale on the left where it says AU. That is to say, it's the astronomical unit, and it is the distance between the Sun and Earth. That's 150 million kilometers. Here you have a much greater scale, because it's 82,500 astronomical units, so much, much bigger than the most distant planet, which might be Neptune, which is at 60 astronomical units from the sun. When we now have a close-up at the end of the simulation, we have a scale which, for the things that you saw before, we have a scale of tens of astronomical units, and these are objects which have a size which is comparable to the solar system. There are some details on this which can be observed. We started with a big one, a light year, which now exceeds the mass of the sun by 50 times, 54, about 10 Kelvin degrees. Here we're 300, but the fall and the collision between atoms of hydrogen releases energy a bit like the anvil, and that's what it works, how it works, because it's the vibration that causes energy, which leads to the fact that the star comes to light or is lit. This infrared, which I showed very rapidly, in 1974, while our Caravel was taking its first flights with the telescope, and we had learnt at the Paris Observatory when I taught. So we learned how to assemble instruments on the plane and to respect very rigorous laws. And in those years we learned something very special and extraordinary. That is to say, first of all, that there would have been on the 30th of June a total eclipse of sun. This is the 1999 one, many years later, which took place and involved Northern Europe across to France. This eclipse was photographed from the space by a French astronaut, by Mira. You can see the shadow of the moon with the haze, because the sun is a very big object which is projected on the Earth, about 300 kilometers in this diameter. It shifts at more than 2,000 kilometers an hour, very, very speed. Speed has to do with the speed of the moon and the rotation of the Earth on its axis, so it depends clearly on the latitude of the observation. But going back to the 73 eclipse, it was on the equator, and this was the most favorable possible point because the movement of the Earth would accompany the movement of the shadow, and it made it for us to it was moving at 2,200 kilometers per hour, so we decided to take advantage of another circumstance. The supersonic 001 Concorde that General de Gaulle and the British government had decided to manufacture as from 1969. Well, this Concorde, the first prototype, 001, it was a prototype which would have then be followed by planes that would be run by the British and French companies. This Concorde had exactly the speed of the shadow of the moon on the Earth. And this was a great temptation for us, using this plane to follow the shadow of the moon. And another favorable circumstance was that the eclipse had been on the day of the solstice, about a week before, in fact, and at that point the shadow should have been on the Tropic of Cancer, which meant that the sun was on the zenith of the plane and very easy to observe under the circumstances. It meant that we could have holes on the top part of the fuselage because to observe, because the outside temperature could have been over 100 degrees centigrade, so it couldn't have been open. We could have boiled water there, which courageous astronomers had done in the 1930s, but with subsonic planes that didn't fly so high up. This was the outline of the research. What could we do? We had to operate to get results. It wasn't enough to run after something like the moon. And so what we did, we had a Zodiac light. Here you can see it on this beautiful photo. This is the horizon from the Chile observatory. You can see the Milky Way, which is observed and is very beautiful. You can see the telescopes and you can see the sunset. It's below the horizon, otherwise you wouldn't see the stars. And then there's Venus, which is about to set. And then there is a line which I have represented as this right eclipse, but the ecliptic, that is to say the plane on which the planets and the sun move, this trajectory is represented by the pink line. This widespread light in this area is what we call the Zodiac light. These are residues of the formation of the solar system. I spoke about the gas, the dust, and the disks that form the planets. And so in the solar system, there are not many compared to the plenty that there were 5 billion years ago, to the amount that there was 5 billion years ago. But these are also deposits of comets who evaporate as they reach the atmosphere and deposit part of the nucleus, such as the comet, which you saw the magnificent images that were broadcast. They're a sort of cluster of dust and ice heated by the sun. Comets release this dust, which then fills the interstellar space. And after the sunset, the light of the sun is seen through this dust, like the dust that you could see from a projector, for example. If you turn the light off in the hall, it would be roughly the same effect. It's interesting to study this, and here you can see the sun without the eclipse, and you can see the comet, which is depositing dust around the sun, and then a sort of area which contains this, but not too close to the sun, because the temperature has gone beyond the pulverization of silicate. So these are silicate, and they vaporize at 1500 degrees. You can't go too close to the sun. They're hot. And they emit infrared rays. We wanted to understand what their composition was to test the hypothesis of the presence of these grains. So one of the two French teams on the Concorde did this. We had 4 windows, and the fifth was the fifth study was through a lateral opening or window. 4 of these 5 had been created for this. You don't make holes on a plane without any precaution compared to considering all the problems. So it was rather a complex process, which we had to perform within 3 months. It was a real feat of engineering. Unquestionably, and we declared after this that the plane could be used. There were 2 teams, one French, mine, and then the other one. They were afraid that our experiment in the atmosphere would have complicated their observations on the ground, but we were careful not to align ourselves with some of their telescopes, with any of their telescopes. In fact, here you can see the trajectory, here you can see the shadow. We took off from Las Palmas in the Canary Islands with a pilot who was really outstanding, André Turca, who is now 92, but who remembers exactly when we took off, the speeds and so on, the speed that we had on the plane. An extraordinary man who followed all the various test flights to then have the possibility to use it. So here there was a specific point a little before the second contact, where we came into touch. We had asked the pilot, we were tolerant, to be accurate to the kilometer and to the second. He said he was going to do his best, but possibly he could have done something even better. We had some test flights to see where we would have landed, or not landed, but have contact with to the second. And this was type of accuracy that we needed today, that human beings are able to put robots at 500 kilometers from the Earth. So this success seems to be a little thing. But 40 years ago, we didn't have any computers. Piloting was from inertial central control units, CPUs, and it was really an adventure to manage to meet all the appointments in the middle of nowhere in the desert of Mauritania. And then once we had respected or met our appointment, then the plane had to respect the protocol, and we had to be careful that the shadow should not get ahead of us. Luckily, everything went in the best possible way, and we followed the shadow for 74 minutes. We could have, in fact, touched 80 if we hadn't had a wind against us. And then we landed in Fort-Lamy. That was the capital of Chad, that is now called N'Djamena. For 74 minutes, we were able, with the 5 scientists and the 5 devices, we were able to carry out additional experiments and measurements. The measurements were very complex, such as the one which I illustrated on the light, which I illustrated earlier on. But you shouldn't try and kill too many birds with one stone, so we did what we could. And this is an image of the plane in flight. You can see that it's dark. I will also show you a few minutes of a film clip that will give you an idea of the atmosphere that existed. It was a Mach 2 with minus zero .5 because it was a plane which was a test plane, and to gain a few additional seconds, the pilot pushed the plane to Mach 2.09, which enabled us to reach the 74 minutes observation. To the right, you can see one of the engineers that worked with me. And these are the instruments with a vertical window and then the mirror which reflected the light of the sun. This photo is extraordinary. We didn't have the time to look from the windows, but I took a few seconds once all the measurements had been taken to go to the window and take this photo, which is unique. Here you see in the forefront, you see the wing of the Concorde, the Gothic wing, as it's called, because of the non-rigorously straight one, and the moon and sun on the African outline. It was a great drought, and you can see there's a very net area with the darkness, and then there's a sort of mixed shadow area, and then sun outside the eclipse area. You can see normal daylight, and you can see troposphere, that is to say the area of the atmosphere below 10 kilometers, which is, as the name suggests, the Greek name says, is very troubled. There are silicates, that is to say grains of sand and other silicates. Above the troposphere, as if it were a lid, at the limit with the stratosphere, which is very calm, which is where we were flying. We were at 17,000 meters above sea level, which is the favorable height to observe infrared because there's no dust, which is why the light is a beautiful blue light, which is that of the molecules of oxygen and nitrogen. That through which the sun rays go. This is the conclusion of the flight when you observe an eclipse from ground in the best possible case, and this is what happened for those who remained on land. You have 7 minutes at the most of total experimentation of the phenomenon. That is to say, you can have it for 7 minutes, while we had it 10 times more. 74 minutes, and the drawing on the right shows what an observer at 3,000 meters could have seen had he or she been looking at the sun. And the solar crown, which we also studied in the course of that eclipse, and the plane which passed right in front of it. I will stop here to show you now a brief clip from a movie that you can find on the internet. It lasts 33 minutes. Obviously, I can't show it all, so I've selected a part. It is called Eclipse 73. You will find it. You'll find it on the net. Here you can see the shadow of the moon. This is a simulation filmed by somebody on board. You can see the plane. Here you can see the pilots in the place in the cockpit, Mach 2 speed, and the plane. WTSS. SS stands for supersonic. Once again, here you can see the horizon, and then immediately after the third contact, the sun after the second contact. Allow me to correct myself. It's a second contact. It's becoming darker, and it's getting darker and darker inside the plane, and we began taking our measurements. Here the plane is in fact overtaken by the shadow that is going a bit faster than the plane, and light comes back. It was a magnificent moment. I hope that each and every one of you could experience it. If you haven't seen a solar eclipse, I hope you will. and that you will be able to see the last one. There's one every 2 years, roughly, but sometimes in areas of the planet which are inaccessible. This is the radar of the plane. No plane was allowed to fly on Western Africa at that time, obviously. There wouldn't have been any risks of collisions or interference or problems in airports, but these were the clouds of the intertropical ones. Here you see that the sort of purpley, but much further south in Niger, and here we're landing. We didn't have at that point much fuel left. We got to N'Djamena. This is the runway, and here you can see the delta-shaped wing in N'Djamena. We were welcomed by a coup, in fact. In the roads, there were machine guns and so on. The evening before, there was a coup d'etat. We were welcomed by a happy crowd, but with armed soldiers. There you are.
Soldats en armes. Voilà. Alors, je passe maintenant à la troisième partie de ma présentation.
Right, I am going to talk about infrared light, but at this point I'm going to be talking about what was done to observe infrared from the land. From land. They're not exactly the same wavelengths as compared to the ones which you can observe in the space with a satellite or from a plane like Concorde. These are shorter wavelengths. It's what we call the near-infrared. And when, for example, you play the piano, you play with some octaves which go from C to E, F. There, usually you don't use many of the octaves, so we have our frequency too. If, for example, we look at the range of frequencies and no longer acoustic ones, as in the case of pianos, and we see that what the eye is able to observe is less than an octave. For example, we have blue and red at the two ends of the visible spectrum. So basically, we have the equivalent of an octave for visible light. But infrared, it corresponds to 8 octaves, that is to say, the entire range. So there is an enormous diversity of light in this field, in this area, which separates the visible waves from the radio waves. So the longer and the shorter ones are both observed and observable from the surface of our planet. And we try to observe them through telescopes, which have to be the biggest possible for 2 reasons. First of all, to be able to put together the greatest amount of light possible, and then to see, secondly, have a greater detail of the image with the big telescopes. So here you can see the observatory that Europe built with also Italy and France and other countries too. And this was a project which we developed at the beginning of the 1980s, and that was approved by the member states of the Austral Observatory, European Observatory. I would like to recall Franco Pacini, who was a member of the Académie dei Lincei and director of the Arcetri Observatory, with another friend from the University of Bologna, played a very important role in the participation of Italy in this wonderful project. It was really an adventure where altogether we saw that Europe had a meaning. had a meaning because it meant that we could attain scientific discoveries that were impossible and unattainable for each country separately. We went to Chile and we went to the Atacama Desert, a desert which is very, very dry without any it's one of the driest points on the whole Earth without any steam at all, and which is therefore one of the best places to receive the infrared light and to see objects which are not too warm and stars. Here you will observe a close-up view of this enormous telescope, which currently is the observatory was for the infrared and the observatory, meaning it's the most powerful one here. They are bringing some new instruments, and these instruments are very heavy. This is the sphere for the observation of the exoplanets. But before this, I would like to talk about the imitation of astronomic images, which was observed by Newton, first of all, and that between Newton and the 1980s, that's a long time, seemed to have been a threshold that could not be exceeded for the observations from the Earth. It was necessary to go into space because this unpleasant behavior of the images, you see that you can't see it properly. It should have been a point that was due to the turbulence of the atmosphere of the Earth, the troposphere I was mentioning earlier on. Now this makes it impossible for you to see detail. Here you can see top left, you can see top right, the ideal telescope according to the side. The bigger the diameter, the more limited diffraction is, and the more accurate the image is. We go from an extended image to a very limited one, and the smaller the image, the more clearly the details can be observed. What happens on the left with the atmosphere is unsustainable, and it has meant that for various centuries, telescopes had to work with images that were not in focus. It was fine to have big telescopes to have more light, but it was impossible to attain the detail and the accuracy which would have been necessary. In the 1980s, we fine-tuned what we called adaptive optics, and which is now found in all the big telescopes in the world. It's without this correction of the images, we would probably receive a deformed wave, but we then mirror it on a mirror and it straightens out. Imagine, for example, a body maker that's mending the body of a car. We can do this. We're in Agnelli's city, and there's the body of the car, and we're trying to straighten the car body out, and there are dents. And this mechanism is rather complex, so you need computers for it, but it's a miracle that it works. And here is the result. The deformed image that we saw before virtually now is stable. For the past 30 years, 25 maybe years, it has improved drastically, and you see the image has the size of the ones listed on the right. There's simply the diffraction of the instrument, and it is the effect of the atmosphere has disappeared. This means that the images are accurate, and in the case of the Chile telescope, we can reach about 20 milliseconds, while earlier on they were only 1 to 2 seconds. So we have gained by a factor of 100, which is a lot in physics in a lab. When you have 2 to 3, an improvement and result, we're very pleased here. We've had an improvement of 100-fold. A 100-fold improvement is really a lot. This technique, which is quite simple, of adaptive optics, it is not particularly sophisticated, but it has generated a revolution in astronomy. Amongst all the astronomical results, I would like to show 2, which are particularly spectacular and which were obtained thanks to this telescope in Chile by European groups, and which concern 2 areas that are particularly important in present-day astrophysics. The first one is the first image of an exoplanet. The exoplanets are the ones such as Jupiter, Mercury, etc., that, however, rotate around a star other than the Sun. Until 1995, we didn't know any other than the ones around the Sun. But thanks to Gilles Maillot and Colosse, who worked with a small telescope in Provence, in France, quite near Turin, in Saint-Michel, at the observatory, we managed to see a planet. A planet which is about as big as Jupiter, quite big, that rotated around another star. 1995. Next year, we will be celebrating the 20 years of the discovery of the exoplanet. These 20 years that have gone by have seen more than 2,000 exoplanets, 15,000 planetary systems. So an evolution which is enormous, with questions that are very important and that we might spend a couple of evenings talking about. I'd like to show you this image. The method developed by Michel Mayer is an indirect method observing the changes that due to gravity the planet has on the star. We were able to identify the presence of the exoplanet. The success is the ability to reproduce the image. Here you can see to the right the star and to the left the exoplanet. This was a picture taken from the Grenoble Observatory near by Anne-Marie Lagrange. She is a French astronomer. With the use of adaptive VLT optics. You see the images are beautiful. There are no deformation. The exoplanet is at 55 astronomical units from the star, roughly the distance which Neptune has from the Sun. 250 light years from the Earth. From this image, which was taken in 2005, was followed by about another 10 exoplanets. And once you have the image of the exoplanet, you can then analyze the light that you've received from the object. And specifically, we can understand what the makeup of the atmosphere is, if there's water, methane, metals. We can therefore identify atmosphere with, say, ammonia might be there, very similar to the atmosphere of the Earth at the moment of formation. Another spectacular picture is something I wanted to show you because it's the Beta Pictoris. Again, Grenoble observed it, and it's the protoplanetary disk. The star has been hidden because it would blind us, but there is a small disk, and we've dimmed that down too, but you can see that there's a point at 10 o'clock if you look at it, compared to the central one. Now let's zoom in. It's a planet. And the planet was questioned by others, other teams, as always happens. wanted to verify what Anne-Marie Lagrange and her team said. The answer was we can't see anything. The answer of Grenoble is you can't see anything because at this point the planet is behind the star. And the other people said that no, they got it wrong, and they said no, the planet will reappear on the other side in 2 years. And here you have the other image 2 years ago. In fact, the planet reappeared exactly where we were expecting it and continued. In fact, we could see the movie that represents its movement. This is something spectacular. A short while ago, I mentioned the fact that there are 2,000 exoplanets that we are aware of, and we're starting to understand that how these planets are formed in the disk, which accompanies the formation of the star. Another photo, which I think is extraordinary, and that was published a few weeks ago, and from the taken at the Alma, Chile observatory. I showed it to you. Do you remember? It's a distant infrared. We're already in the radio waves. HL Tauri is the name of the star, a bit further than the sun, and you can see that the planetary disk has sort of grooves like an old vinyl record, and these grooves are the traces of the planets that have been formed, and there are different ones at different distances from the star, and which have absorbed the dust and silicate that was scattered. Now there are no more. There's no more dust, or because they've coagulated in a planet, you can't see the planets because resolution isn't good enough. But unquestionably, astronomers will be looking for them, because this is the moment, exactly when, and we can date the formation of the disk to 1 million years after the star came to light, so to speak. Immediately after the formation of the star, the planets also were formed. Statistically, we can say that in our galaxy, and probably also in the others, there are on average at least one planet around each star. Some have 10, some have none, but on average, all the stars have exoplanets. This has transformed our vision of the universe. Another comment on a result which is obtained thanks to adaptive optics, which is the discovery of a black hole. This was discovered by the Max Planck Institute. This was Gensel, and he discovered this. This is a simulation describing cluster of stars, a very rigorous one. All the positions have been measured and plotted. Here you can see this video, which represents the movement of stars around a black hole, which we can't see by definition, but which is at the center. The movement of the stars makes it possible to identify or determine this mass, but very few thousand kilometers. These are figures that go beyond our imagination, but go beyond also the physics that we carry out. The field of gravitation around a black hole is so intense that in these artistic depictions, the central part is not visible, while in the non-visible part outside the horizon of the black hole, there the matter that is absorbed into the black hole reaches very high temperatures. This is an interstellar representation which it's also been shown at the movies now, talks about the properties of gravity in the areas close to a black hole. it's unlikely that a traveler, a space person, could resist the temperature of this black hole. In any case, these are two aspects of contemporary astrophysics, exoplanets on the one hand, and physics of the gravity field, of the intense gravity field on the other, that are two concepts that we've been able to develop thanks to our adaptive optics. Astronomers will not stop thanks to these very good results. Here you see the European Extremely Large Telescope. About a week ago, the ESO Council, with 8 countries, the 8 countries that has now started with 8 countries, now has 15, maybe 16, when, for example, Brazil will join the project. I was saying the ESO Council has just approved the building of a 39-meter telescope in Cerro Armazones. This is a rendering. The machine gives us an idea. Sorry, the cars that you can see in the front give us an idea of the proportions. The mirror is made up of hexagons. It can't be just one piece, and it will be completed by 2024, in 10 years. This telescope would not have been possible if we didn't have adaptive optics. I would like to now take a few minutes to speak, in the very few minutes I have, that in France, it is said the scientists are like big babies. I don't know if you have it in Italian or English too as an expression, but very often there's a truth in these sayings. What does it mean? It means that scientists, in their everyday work, for the joy that they have in work and discoveries, have maintained a quality which very often many adults have lost in the meantime. That is to say, curiosity, surprise, the ability to be surprised, faced with the beauty of the world, of this world which have been given to us so that we may observe it and understand it. What can we do? We have to try and develop curiosity amongst children that have questions. Why is the sky blue? Why are plants green? And they also make hypotheses such as the scientists do. Some of these give us the idea of a big imagination, rather odd sometimes, and while others are very accurate, and it illustrates how children can think things which are very complex. This was the intuition of the physics Nobel Prize winner, Georges Charpak, who was mentioned by Piero Bianucci. And in 1995, he launched a movement which is called La Main, la pâte, that is to say, hands-on, which was first French and then European and then world, which has 3 aims. Primary school, reading, writing, and arithmetic, and then in the past century, this has been attained, and we have to add another task, that is to say, think. The ability to understand. Reading, writing, and maths are all right, but you have to also understand. And this is the aim of the hands-on. We worked with our friends in Italy too, with the Académie dei Lincei. And here you can see the association, which is called anisn.it. And we created a program in Italy that works through them in Milan and Turin, and a program with which we're trying to develop at school the ability of children to imagine and think and draw conclusions and express this in a beautiful with beautiful words. Astronomy is very well suited to this type of exploration, to the exploration of nature, and I would like to show you two pictures to conclude. One is a school of the Jura in France, where the children are putting equipping their computers with a small telescope like Galileo's to observe the moon, to see how the distance between the moon and the Earth changes. And the same tool, not exactly the same tool, is also being used in Asunción in Paraguay, a very poor area where the children, with the same type of happiness, with the same questions, the same enthusiasm, observe the beauty of the sky and the science of the sky. It's a very beautiful adventure that I was able to experience, and I have been experiencing for the past 20 years, and I'm very pleased to mention it this evening because I think that it is the best thing we can leave our children, the best thing that we can leave our children. Thank you very much for your attention.
Je vous remercie de votre attention.